Welcome to Math Shorts, tantalizing mathematical tidbits that will amaze, entertain, and delight. Math Shorts is brought to you by the Ottawa Zone for Mathematics Education. The Ottawa Zone for Mathematics Education is a chapter of the Ontario Association for Mathematics Education. Information about both organizations can be found in the information for this video. In this episode of Math Shorts, we'll be investigating the perpendicular bisector of a line segment, its properties, and some of the consequences of these properties. First, we need to know what we're dealing with. The perpendicular bisector of a line segment AB is a line that passes through the midpoint of AB, that is, it bisects it, and is perpendicular to it. We see in this case that the name perfectly describes the object. At this point, we should ask, what are some of the properties of this object? A basic and very important property of a perpendicular bisector is that any point on the perpendicular bisector is equidistant from the endpoints of AB. Now, what does this mean? It means that if we take any point on the perpendicular bisector, P, and we join it to the two endpoints, then the distance PA and the distance PB should be the same. In mathematics, we spend lots of time searching for patterns. When we find these patterns, it's important to try to justify or prove that the pattern continues and it isn't just a fluke. In our case, if we examine the two right-angled triangles, PAM in yellow and PMB in orange, we know that the sides AM and BM are the same length because M is the midpoint of AB. We also know that they share a side PM. So if we use the Pythagorean theorem on these triangles to calculate the hypotenuse on one of them, when I go through to do the calculation on the other one, I'm using exactly the same two numbers in my calculation. And as a result, we're going to get the same value, which means that PA and PB are the same as we stated. Those of you that know a little bit about congruent triangles, we could have done this a different way. If we look at the two triangles, we've got a side, an angle, and a side that are equal in the two triangles, which means the triangles are congruent, and therefore all of the pieces match up. As a result, if we look at the big triangle, PAB, we see that it's an isosceles triangle. And since it's an isosceles triangle, we're going to have these two base angles equal to each other. Now, an important thing with an isosceles triangle is if we do the perpendicular bisector of the base, and in an isosceles triangle, when we talk about the base, we're talking about the side that isn't one of the equal ones. Notice that that goes through the midpoint and through P as well, which means that PM, which is the median from the apex, and the apex is the vertex between the two equal sides. The perpendicular and the median, as well as the altitude, P to M, is perpendicular, so it's the altitude going to the apex. And if we go back to our little triangles, we notice that we have all the sides are equal, two of the three angles are equal, which means that those third angles have to be equal, which means that PM is also the angle bisector of the apex. And it turns out that if I have an isosceles triangle, all three of these things, or all four of these things, coincide. They're on top of each other. The perpendicular bisector of the base, the median from the apex, The altitude from the apex and the angle bisector of the apex are all on the same line. Now this is all fine and good. We know some properties of a perpendicular bisector, but how do we actually make one? Well, if we had a line segment, we could use a ruler to figure out where the midpoint was. We could use a protractor to make a 90-degree angle, and we could come up with our perpendicular bisector. It won't be entirely accurate, and there's actually a better way we can do it using a geometric construction. So suppose we have a line segment AB, and we draw a circle that has center A and passes through B, like this. And then we sort of flip things over and draw a circle with center B that passes through A. So those circles meet at 2 points, P and Q. Now, I'm claiming that those points are actually on our perpendicular bisector. So let's take a look at why that should happen. We know that everything on the yellow circle is equal distance from A, because A is the center of the circle, which means that from P to A and from A to B are exactly the same length. Similarly, everything on the orange circle is equal distance from B, because it's the center of the circle, which means that P to B and A to B are the same thing. But notice in both cases, AB was part of that process. What that really means is that P to A, P to B, and A to B are all the same thing. And since we are after the line segment AB, all that we really care about is P to A and P to B. Those two things are equal in length, which means that P is on the perpendicular bisector. Now, those of you that are observant will also notice that this process, we've created a triangle where all the sides are equal to each other. And this is actually a way to create an equilateral triangle using a compass and straight edge. So, just sort of an interesting byproduct of our process. So, we can go through exactly the same thing. Q is going to be equal distance from A and B as well, and ABQ would also be an equilateral triangle. So if we draw through a line through P and Q, that's going to be our perpendicular bisector of AB. Okay, let's take a second and do some investigation with some dynamic geometry software. I'll be using GeoGebra because it's available online for free. There's lots of other options like Geometry Sketchpad. If you haven't used a dynamic geometry software, I strongly suggest you check one out. It lets you play with geometric properties in a very interesting way. So let's look at that last construction of the perpendicular bisector by using circles. So suppose I start with a line segment, maybe, and we claimed and showed that if we take a circle centered on A that goes through B, and a circle centered on B that goes through A, then those 2 points where it crosses, let's make that a little smaller so we can see it. Let's make those 2 points where it crosses should be on our perpendicular bisector. So let's go to the point tools and go down to intersection. So if I click on where these things cross, it'll make a point at those intersections. So we claim that those 2 points should be on the perpendicular bisector. Now, the neat thing with GeoGebra is a lot of these tools are built in. If I go back to the point stuff, down about halfway down is there a tool for midpoint. If I click on it, if I either just click 2 points, it'll show me the point that's halfway in between them, or if I have a line segment, it'll give me the midpoint of it. So there's my bisecting point. If if I could get a perpendicular line, and up in these tools here, there's one for perpendicular line and actually perpendicular bisector if you want it as well. So if we go to perpendicular line, I select the line and the point you want it to go through. There's my perpendicular bisector, and it passes through those two crossing points as we saw. Okay, no big whoop, but let's do something else. So let's just sort of take these let's sort of take our two circles and make them a little bit less noticeable. And I'm going to create a little line segment off to the side. And notice it calls this H. That'll be important for us in a second. And I'm going to go back to my circles, but instead of creating a circle with center through a point, I'm going to create a circle with center and radius. So the first one, basically I need 2 points, the center and some point on the circumference. For this, I need the center and a number for the radius. So if I click on A, I could type in the radius as some number of units, or I'm going to use the name of this line segment H so that I create a circle with center A that has radius equal to this. And I'm doing that so that as I change this, I can create circles of different size centered on A. Now I'll do the same thing for B. Pick that as our center, use H as our radius. And so I've got these 2 circles, one centered A, one centered B, but with the same radius. Now this is going to show that we don't have to use the circles centered A that go through B and centered B go through A. All we need is 2 circles centered on those 2 points that are big enough to cross. Because if I make these a little bit bigger, eventually they get to the point where they just touch. And when they're big enough just to touch, they touch the midpoint, which is on the perpendicular bisector. And if I make it any bigger, notice that the 2 points of intersection are always on that perpendicular bisector. So we can create the perpendicular bisector by just drawing 2 circles that are the same size, centered on A and B, that are big enough that they're going to cross. We're not stuck with the one through A, with center A through B and center B through A. The reason we do that is because those are convenient ones. That's obviously always going to work, but it's not necessary. There's lots of them that work. So if we want to construct a perpendicular bisector of a line segment using a straight edge and a compass, it's not necessary to draw the full circles. We can get by using only arcs. That is, we know that it's going to go through the midpoint, so we don't have to draw the full circle. We can draw the part of the circle that is near the midpoint, above and below it. And if we do similarly with the other circle, drawing those 2 arcs, where those 2 things cross are going to be our 2 points P and Q, and we get our perpendicular bisector. Now, what's a consequence of some of these properties? Well, another important one is that if you take the perpendicular bisector of any chord of a circle, so I've got a circle, I take any chord, the segment joining 2 points on the circumference, and I do the perpendicular bisector. Since we know that any point on this perpendicular bisector is going to be equal distance from those 2 points, and we know that a circle is the set of points that are equidistant from a point called the center, that means that the center of the circle has to be somewhere on this perpendicular bisector because it is equal distance from A and B. So if I take that chord, the perpendicular bisector passes through the center. If I take another chord and find its perpendicular bisector, it passes through the center. If I find another chord and find its perpendicular bisector, it passes through the center. Let's zip back to GeoGebra and see this property in action. It says that if I take any circle at all and I find any chord of that circle, so I'm going to select point on object so that I can pick 2 points that are on this circle and then go to a segment and draw in a chord. I can use my moving tool to move these labels as well as if I want. Now let's see what happens when I find the perpendicular bisector. Now we saw that there was a perpendicular bisector tool right there. If I click on that line segment, patau, and there we see it goes through the center. And here's one of the powers of using dynamic geometry software, is now I can see that property in real time. As I change the location and the size of my chord, we see that it always goes through the center. Even if I change the size of my circle and its location, I always get that chord going through the center. And so the dynamic geometry software like GeoGebra is really cool for taking these geometric properties, sort of building them into a sketch and seeing that they don't change even as you change the objects that are involved if you've got a specific property. As a result, if we have a circle and we want to find its center, all we have to do is find the perpendicular bisector of 2 chords and find out where those 2 things cross. So for instance, if I draw a chord AB in a circle and find its perpendicular bisector, I know that the center is somewhere on this line. And now all I need is one extra point, C, because now I can use BC as my second chord. If I find the perpendicular bisector of that, I know that the center is somewhere on this line, but it has to be somewhere on this line. So as a result, the point of crossing is actually going to be the center of the circle. Now, you may have noticed that we've kind of got one extra chord here, and if I joined up A and C, because the center is on the perpendicular bisector of this one as well, because it's equal distance from A and C, I've created a triangle within a circle. Now you might ask yourself, is this always possible? And it turns out it is. And we get one more interesting property of perpendicular bisectors. Now, perpendicular bisectors that are associated with a triangle. That if I take the perpendicular bisectors of all 3 sides of the triangle, they're concurrent, which means that they pass through a common point. So let's see why this should be true, or even prove that it's going to be true. If I pick one of the sides and draw my perpendicular bisector and do the same thing for the second side, I know that those things are going to cross. Now, if I look at that point of intersection and go back to my first perpendicular bisector, by properties of our first property of the perpendicular bisector, we know that that point is equal distance from A and B. Now, if we look at our second side, we know that since that point is also on the perpendicular side, bisector of BC, that it is equal distance from B and C. But the distance from B is already the same distance from A, which means that the distance that that point is from A and C is equal distance, which means that that point has to lie on the perpendicular bisector of the third side, which means that no matter what we start with, all three perpendicular bisectors of the sides of a triangle are going to cross at a common point. Now this point is called the circumcenter, and the reason that's called the circumcenter is you notice that that is the point that is equal distance from A, B, and C, which means that if I draw a circle using that as our center, I can draw a circle that goes through our triangle. And that point is called the circumcenter, and the circle is called the circumcircle of the triangle. Let's finish off by returning to GeoGebra and looking at that last property. It said that if we started out with a triangle, by just taking three segments, joining them together, and we do the perpendicular bisector of each of the sides, boom, 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 those all cross at a common point, as we saw. And if we move this around, we see that the point moves around, but that those three things always seem to cross at a single point. And again, that's one of the powers of the dynamic geometry software, is you can see these properties in action. Now we went and did more than that. We said that if we find out where these things intersect at that point, and we said what happens if you draw this circle, that circle with that center, I should be able to find a circle that goes through all 3 points. So let's make it go through A, and look what happens. It goes through B and C. And again, as I change my points A, B, and C to create new triangles every time, every new triangle shares that property. We get a circle that goes through those 3 points, and the center of that circle is that common point of intersection of our 3 perpendicular bisectors. I hope you've enjoyed this episode of Math Shorts. Check the video description, and I'll leave a link for GeoGebra for those of you who are interested in checking it out. Check out the channel next month for our next episode. Till then, keep thinking.